Here we have a problem in which we have a rubber band which at its maximum unstretched length has 0 tension. Stretched by 5 centimeters from its unstretched length, we have a 46 Newton tension. If stretched by 10 centimeters from its unstretched length, a 76 Newton tension. 15 centimeter stretch, 102 Newton tension. Now we attach a 1.33 kilogram mass to the rubber band when the rubber band is stretched out by 8.8 centimeters. The mass is released from rest, V0 equals 0 at release. The rubber band snaps back and the object reaches some velocity at the instant the rubber band reaches its equilibrium position. The question is, what's that velocity? Well, we know, let's look again at what we have here. We know that the rubber band is exerting force through distance. The distance is 8.8 centimeters. The force, however, starts out, well, definitely over 46 newtons, since a 5 centimeter stretch gives us a 46 Newton tension. An 8.8 meter stretch will give us more than 46 newtons. And less than 76 newtons, because it takes a 10 centimeter stretch to give us 76 newtons of tension, and 8.8 centimeters is less than 10 centimeters. The force keeps changing as we move from here to here. And it changes in a way we can't really define precisely from these numbers, unless we know something more about the rubber band. However, what we can do, we can estimate the average force. If we multiply the average force by the 8.8 centimeter distance, then we should get a good estimate of the work done as the rubber band snaps back. Here's a graph of our data. A 5 centimeter displacement gives us a 46 Newton tension. 10 centimeters gives us a 76 Newton tension. 15 centimeters, 102 Newton tension. So here's our graph of force versus position, or versus stretch. Excuse me. Now, we estimate at 8.8 centimeters, actually the original number is 8.75 centimeters, but I rounded off to 8.8. I'm not being real consistent with that here. That maybe should read 8.8. At 8.8 centimeters, which is a lot closer to 10 than to 5, the force will certainly be closer to the 76 newtons than to the 46 newtons. By doing some intelligent interpolation, and then noticing that this curve is concave downward, it's kind of humped up like this, in other words, we make our best estimate that the force here ought to be about 71 newtons. Now, if we have a 71 Newton force at 8.5 centimeters, the question then becomes, what's the average force between 0 and 8.75 or 8.8 centimeters? Now, the force is originally 0, so the force climbs from 0 to 71 newtons as the stretch goes from 0 to 8.8 centimeters. At the halfway point, if the curve went along the straight line, and it doesn't, it goes up above the straight line, but if the curve went along the straight line, the average, or the midpoint force, would be 35.5 newtons, half of the 71. Halfway from 0 to 71 would be 35.5. Since the curve humps up a little bit, we're going to say that the average force is probably a little more than the average of the initial and final forces. That average would be the average if we followed this straight line and we're above the straight line. So we're going to say, okay, instead of 35.5, let's call it 37 or 38. And I think we decided on 38 newtons for the average force in this case. Now, if a 38 Newton average force is exerted over a displacement of 8.8 centimeters, how much energy is involved? Well, the work done by the force is the average force times the displacement. The displacement, of course, is parallel to the force in this case, as it must be to use this relationship the way we've used it. Average force of 38 newtons, 8.8 centimeters is 0.088 meters. We multiply those and we get 3.4 joules. So the work is 3.4 joules. If there are no dissipative forces, and that's our assumption here, that we're not dissipating any energy, if there are no dissipative forces as this thing snaps back, then that will be the kinetic energy. Since it started from velocity 0, the change of kinetic energy will be 3.4 joules. Change of kinetic energy is equal to the work done when there's no dissipated force or potential energy changes. The change in kinetic energy being 3.4 newtons and the initial velocity being 0, so the initial kinetic energy is 0, means that the kinetic energy is going to end up 3.4 joules. So that the 1/2 mvf squared for this block or object or whatever it is will equal the kinetic energy, which equals the delta W. So that the final velocity, solving by multiplying through by 2, dividing by m, we get 2 delta W over m. And we take the square root of that, we get our VF. If we plug delta W equals 3.4 joules, m equals 0.133 kilograms into this solution, we get 5.1 meters per second.